Okay, advanced matrix wrangling. This is wizard level matrix multiplication skills. So we've got this idea of a dot product being the basis of matrix multiplication, right? That's our definition. So let me just reprise some of that, and then I'll go through some really important variations on or ways to because this is a very detailed kind of operation. So there are ways to see it in a bigger, broader picture, see multiplication in a bigger way, make yourself able to kind of move through things in a faster way. So the column picture, which we've talked about for x equals b, is very much part of that. We'll see that here. And right, a couple other things. All right, okay. All right, so we'll have inner and outer product. So inner, this word inner is the word we're replacing dot product with, mostly, because outer turns out to be a thing. And it's not really a good opposite of dot. So inner and outer, these are good things. So what's an outer product? Well, we'll see in a second. Okay, we have, this is the ax equals b story, right? So we'll see this is our column picture kind of approach. This thing, y transpose b, so what is that? So transpose we haven't quite talked about, but it is a flipping of a matrix. Just for now, you can think of, if you take so vectors for us are always defined as columns, right? So they're columns. And the transpose version will be just lay it out as a row. So if we have a vector like this, we always put this is T for transpose. We always, right, if we want to indicate we have a row vector, we actually write a vector and a T for transpose. Vectors are by default columns, always true. Okay, so we've got this character here, and then we've got, just in general, what happens with a times b. So there are a couple of ways to advance our thinking there, and then block multiplication. So there are all sorts of ways of actually then constructing or structuring a multiplication of two matrices that helps you with whatever problem you're working on. So this is from before, because I can copy and paste things. Our definition, so C equals A times B, that's okay only in this case, right? Where we can have any outer dimensions, and they go to here for C, but we need to have the inner dimensions match, right? So this is the number of, so it's rows, columns, right? So the number of columns of A has to match up with the number of rows of B. Very, very important. Good. And then our definition was that's the ith row of A, the jth column of B, their inner product. So the inner product is the ijth entry of C. Okay, and there's this nice picture view of it. All right, so let's move on and start thinking about. So we'll just do one product to start with. We're going to work with this little pair of matrices here a couple of times to lay out our examples, or sort of versions of them, right? Yeah, pieces that are extracted from them. So the dot product version, right, if we were just going to do it purely by the definition, so we take, right, the first row, the first column, take their dot product. So let me maybe blow these things out. So if this is A, and this is B, then we would say C11 equals, we could write it out, it's the dot product of this. It's 3, 0, 2, minus 1, 2, 0, right? So this is the first row of A, and this is the first column of B. Right, so I'll just do some little side notes here. So we know how to do this, right? So it's 3 times, right? 3 times minus 1, it's minus 3, plus 0 times 2, 0 plus 2 times 0. Those zeros are very helpful. So that's minus 3. And that's going to be C11. Now here's a thing to think about. Well, let's put that here. So this is minus 3. How big is C? How big is C, right? So we always, don't always, but I'm going to suggest you do this as much as you can, just to, right, so 2 by 3. 2 rows, 3 columns. 3 rows, 2 columns. So that means we end up with, what is it? 2 by 2, right? So we end up with a 2 by 2. And that's this guy here and this guy here. And the 3's match up so we can do dot products. Okay, so if you go through and then so it would be the first row dotted with the second column. That would give you C12. So let's maybe write out here. C12 is 302. And then it's 012. Right, so there's a 3 times 0 plus 0 times 1 plus, so this is all very nice, isn't it? 4. Right, this is C11, C12, and then the remainders, well, might as well write them out. Okay, so C21, which is in here, C21, and C22 is down here. C21 is equal to, let me get rid of that, that. So C21, now we're taking the second row, so, right, 2 here, it's the second row. And we're taking a dot product with the first column, that gives us C21, and then we take a dot product with the second column to give us C22. So let's, all right, let's write it out. Okay, good, good. It's 1, minus 2, 2, and then minus 1, 2, 0, first column. And C22 is that same row, it's the second row of A, dotted with 0, 1, 2. Second column of B, right? So there's we just go through, it's minus 1, there's a minus 4, and then a 0. Good, so this is a minus 5. Let's see if we can get it right. And then there's a 0, and then minus 2, plus 4. So that will be a 2. So I think I've got a minus 5 and a 2. All right, so that's our answer. Where's this thing going? Yeah. Okay, that's the very work person-like way to do it. We'll just march through it. We're going to get there, but we want to, do things in more powerful ways. Let's just think a little bit more about the inner and what we'll see as the outer product first. So let's do that. So that was example 1. Example 2, we've just done it, but it's sitting here. So this is actually taking 2 rows. So if someone gave you this to work on, 1, 2, minus 1, this is fine. This is the, right, this is the matrixology version of the dot product from calculus. Just throw up in my mouth a little bit there. Okay, yeah, we try not to talk about it. Okay, so it's a simple thing. Again, it's defined as dot product. So that's fine. This is okay. This is a weird looking thing, but it's fine, right? So this is it's 1 row by 3 columns, 3 rows by 1 column. So these match. And what's it give us? It gives us a 1 by 1, which is a we're going to say is a number, right? So this is a 1 by 1, and it's just that dot product. So it's 1 times 0 plus 2 minus 2. Maybe I didn't use exactly the same thing. In fact, I wanted to write a minus 2 here. Yeah, so 1 times 0 plus 2 and then plus 2 again. So this is a 4. Right. That's the right. That matches up with. Well, okay. Fine. So this is an inner product. So this is a very lovely kind of way of encoding these things, and we use them over and over again. So example 3, all that matters is the inner dimensions match up. So we could do something. We can now do kind of weird things, right? So we could actually, they don't commute, they don't give you the same thing, but we can shuffle these two. And this kind of construction, as we get to the end of the course, we will see this is incredibly important, right? So this is an amazingly important, it looks weird, but it's an amazingly important construction where you have a column vector right, will matter. And as we go on the course, these things happen over and over again, all right? I know I don't want you to pop. I don't want you to get too excited, but I've got to tell you, there are amazing things happening, right? So this is called an outer product, and it's fine, right? This is fine. This is a weird thing, but this is fine. This guy here is a 3 by 1, and this is a 1 by 3, right? So these things match up. Let's blow it up, right? So this matches, right? And we end up with what? A 3 by 3. I've got it. That's just no good at all. A 3 by 3. Okay, so let's make our 3 by 3. Let's make it. Right? We'll put the shell of the thing down because we know where we're going. Okay, so it's a 3 by 3. This is what we're going to call an outer product. Yeah, it's an opposite day kind of thing. Well, these so it's still made up of all these little inner products, right? So which is kind of a weird thing. So if you want, what's the first entry here? So this is a 3 by 3. The first entry here has to be the first row, right? So let me do it like this. The first entry here is the first row dot product with the first column. Well, it's just two numbers multiplying each other, right? This is a row, this is a column, 0 times 1. So that's all well defined. So let's do it. 0 times 1 is 0. All right, 0. Then we have, if we just go across, right? So we need the next one is going to be the first row times second column, and then the first row times third column. So let's do that. So that's actually, it's 0 times 2 and 0 times minus 1. So we get 0, 0, 0 there. Interesting things are coming, yes, always. Now the next one is, it's really it's the second row times all of these guys. Okay, so let's just do that. I want to step back and think about these things a little bit. So 1, 2, minus 1, because it's just 1 times those. And then the last one is minus 2 times all of those entries. So that's minus 2, minus 4, and 2. A very important thing to think about is we only had six numbers here. Now we have 9. So that seems like there's probably not that much information. Like, how do we make more information, right? And in fact, there's a bit of there's a 0 here, but these two rows are multiples of each other, right? And in fact, they're just multiples of this original row. So, and it's just 1 times that row, and then, right, 1 times that row, and minus 2, and 0. Boom, boom, boom. But let's look at it another way. This is actually, if we go down here, this is this column, right? 0, 1, minus 2, 0, 1, minus 2, 0, 1, minus 2, and 0, 2, minus 4, just multiplied by these 3 numbers. So we have lost information, right? They're all the same. These columns and these rows are multiples of each other. So this outer product, very important thing, but so it has these oddnesses. Eventually we'll call this a rank 1 matrix. Later. See, this is thrilling. And rank has a special thing, R equals 1 matrix. More is coming. There's always more is coming. Okay. So let me just write out what I said just then. So we see that all of this is equal to, I'll write it like this. It's 0 times 1, 2, minus 1. Just fantastic. 1, right, times 1, 2, minus 1. We can put matrices within matrices. Exciting. Minus 2, right, it's inception. Math is full of inception type things. And pretty strange people. So this is 1, and we can do it this way. 1, and it's 0, 1, minus 2. So it's actually, you can kind of skip, right? You can skip this. We didn't have to do all those little dot products. You just say, oh, just take that row, just copy it, and multiply by 0, 1, minus 2. Or take that column, copy it, multiply it by 1, 2, minus 1. Yeah? Good? Right? I have trouble drawing the bottom here. So there's 1, 2, and then a minus 1. So we can see we could write it like that. Right? That's pretty awesome. Yes, it is. Yeah. Okay. So that's good. I'm going to talk about two kinds of so block multiplication, inspired by all of this. You can start to do some pretty weird things, and then we'll go back out to these AX and YA and AB, these bigger stories. Okay, so that was pretty great. I think it was great. And example 3. So again, example 4. So these are really, really, really important things. Okay, this is inner products, outer products, hugely important. Of course, we started off with just the basics there. Example 4. So this is trying to give you power, right? More power, always good, good. Right, we are here. So let's go back to our matrix that we had here. So it was just minus 2, 2, 2. If I get the right thing. Yep. And 1, 0, 2, 1, 0, 2. Now you can start to block it in different ways. So this is block. This is like block. And that, depending on your problem, can be very helpful. Okay. All right, so the idea will be, okay, let me, so we could do this in different ways. So one example is to say, let's block it like this. So these are, now this is a row, now we've got this is a row of 2 by 1s, right? And this is a column of 1 by 2s, right? One row, 2 entries. That's it. So somewhat surprisingly, we can do this. I don't know what I'm doing here. Okay, so somewhat surprisingly, we can do this. I mean, hopefully you believe me now. Right, so there's just these 3 blobs here, and then 3 blobs here, and this is like a big inner product. I'll leave that in. Think of this as a big inner product, so it's really just, it's going to be this 3, 1, 1, 0, which is fine, right? That's a healthy thing. So as long as we break each matrix up in the right way, then we're okay. And then 0 minus 2, right? So this one, and this one, 2, 1, plus these last 2, and these are of course now what we call outer products, right? So I mean, we are making more work for ourselves perhaps, but these might be more useful structures, and indeed that's really true. It's often, this is a place we might want to stop, but we'll get to that later on. So we'll do these outer products, and if you can just think about it in the way I just showed you, let's say this is 3 times this row and then 1 times this row. Just make copies of them. That's the fast way to think of it. So 3, 0, 3, 0. I'm just multiplying that row, and then 1, 0. Same thing. So now we want 0 of the row, 0, 0, minus 2 of the row, minus 4, minus 2. And now we want 2 of the row and 2 of the row, stacked on top of each other. So 0, 4, 0, 4. And we add everything up, right? 3, 0, 0, 0, 0, 4, and then 1, minus 4, which is hard to understand. I think I've got I may have left did I leave something? Did I do something bad? Yeah, I did. This is a minus 1. Okay, bad behavior. So let's fix it up. This is what happens. That should be a minus 1 there, minus 3 there, minus 1 there. Yeah. So we've got a minus 3, minus 5, and 2. That's not the case here, but there are a lot of problems where you can really check. You get an answer and you can check. So we knew the answer, so I could stop my insanity, but always do that. All right, so that's peculiar actually, right? So this is odd. So another example would be, let's write it down again. So let's call this, okay, we'll call it example 4, example 5. Let's write another one, very similar kind of idea, but we're going to break it up in a different way. So we could say, I'll frame it as matrices inside matrices, because I'm sure you're excited about that. 2, 2, right? So if we do this, now we've got 2 blobs, right? This is actually just 2 entities here. And as long as we have 2 entities and the dimensions match up, so -1, 0, 2, 1, that's okay. And then a 0, 2 at the bottom. So we can do that. And so we'd have, right? So now it's just, here's a blob, here's a blob, blob, blob. Okay, get rid of those things. That's all right. And we need an extra thing here. So this is going to be 3, 0, 1, -2, -1, 0, 2, 1. So that's well defined, plus an outer product, 2, 2, 0, 2. This thing, as we now know, this is a 2 by 1, a 1 by 2. So this makes a 2 by 2. So they can be added together. So everything works out. That's nice to see. And again, we get the same result. Okay. So that could be that can be a useful thing. As long as you break it up, break both matrices up in ways that match still, you're fine. All right. So now let's go and think about AX. No, I have this written out already. So I just want to walk through this. AX, very important, right? This is our frame that we are following through all the way. Maybe I'll just leave it red. Right, so it's got to be n by n, n by 1. The inner product, the inner pieces have to match up. That's good, and we end up with an n by 1. Right, so the result is an n by 1. Okay, so what's the way to think about this? So we've got n rows here, n columns here. Those things match up. Right, that's the right shape. So we see this, so we're going to look at this and see this as columns. This is this block structure, columns, right? Maybe like this, columns, boom, boom, boom. And then they match up with these entries here. And that's what this structure is now. So, and there's a particular kind of formalism that I've used, which is this A star 1. Right, this means, I mean, it's written over here, but run over all the indices, right? So this is a column vector. It's, in fact, the first column vector. So it says star just means like a wild card, if you like. So run over everything. So we'll always write in this form. So I'll just put the A there and then put a line above and below to indicate that it takes up that column. And we'll see, we'll do the same for rows. So now this is a block matrix problem, right? Because we have simply n entities here. This is like a big inner product. And then we have n entities here. So we just take them one at a time. And because these are just numbers, right? x1, x2, we would normally, it would be normally, let me say, this guy inner product with this guy. But because it's just a number, we can slide it over to this side. So this is what we were doing with Ax equals b. It fits in with this bigger picture of matrix multiplication. So now we get, x1 times the first column, x2 times the second column, x7 times the seventh column, and add them all up. And this is a better way to think about things. So the example that we've been working on, just taking part of its structure, right? So now we have, right, normally we could just sort of just do these two dot products, right? But actually, it's better to think, let's break this into these three entries, three objects, and then again here. So we're going to end up with, I'll leave it there. So the -1 is here, times this character, and then 2 times 0 minus 2, and then 0 times 2, 2, right? So that makes sense. All right, so now we've got columns. We're scaling them, right? So these are scalings. Yeah. And these columns, which I kind of like you to think of as maybe musical sounds, are then being turned up and down in volume, and we're adding them together, and of course we're just adding these multiples of columns, so we end up with the same size, and we get this -3, -5, right, which was the first part of that product. So that's an important thing. We'll use that over and over and over again. There's a natural way of doing this from the other side, and I'm going to introduce very sort of sneakily here this notion of a transpose, right, which I mentioned at the start, but there's a little t here. So just to start with, for vectors, just think of it as that turns it into a row vector, right? So we take it and then we wrap it up like this, and so the entries just read across instead of down. So that's what we have here, right? Y by itself, just the y vector, is a column vector. The t says run them across. Now we need m entries, because this is now, this A is an m by n, right? And y transpose is a 1 by m, 1 row, m entries. Y is in fact an m by 1. Oh yeah, I've written it underneath. Right, y is an m by 1. MB, I guess no one knows what that is anymore. Nota bene, note well. All right, so same idea, it's a block structure, and I'm going to get rid of that and put in, right, so we've got entries, 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 then we've got these ones. So it's a big inner product, and it's y1 times this first row vector in A, y2 times the next row vector, and it's got that same structure that we had over here. So A1 star, so again it's a wildcard, so this is the first row vector in A. This is a sort of stylized way of representing it. You might see in books like you'll just see A1, right? So you might see this guy over here just written as A1, fair enough, but that's not good when you start to say, well, what's the column thing? So we need a slightly, some of my notation will differ from strings actually, because I want to make things really clear in my own special way. All right, so let's see. So as I said, it's an inner product. So all of this just becomes, right, the first entry, y1 times the first row. And I'll kind of write them like this is a stack here, but it's really just a row vector times a number, row vector times a number, row vector times a number, scalings. And so we're going to add all those row vectors together. Right, and so it's written out here, right? So these are the rows, they're being dialed by these, the weights that are contained in Y. And so here's one example. So here's a nice row vector. Here's our A matrix. And so it is 3 times the first row, that's here. Then 0 times the second row, that's here. 2 times the last row, here. Add all of those things up, all right? Put in the right things, and we get -3, 4. And you can, of course, you can do this by just doing dot products here, right? But it's really, this is a really important step up behind simple inner products for each element. Okay, so there's this is starting to get us, so there's something very special about this, right? The Y's kind of exist on this left-hand side, the X's are on the right-hand side. Lots more will come out about that later on. So I can see where those Y's live. Interesting. All right, so C equals AB, so now we're talking about matrices. Let's bring this up. This is the last piece that we're going to go through. Right, so we have the right things here, m by n and m by k. I guess I've switched it here, but this is m by n and m by k, so those two, the ends match up. So we end up with an m by k. So we can use what we've done so far, we can break B into columns, or we could break A into columns, because we know stuff on the right-hand side are best thought as columns, because that's how the inner product works, and the things on the left are best broken into rows, because again, that's how the inner product works. So let's take B, break it into columns, and then you can do this rather magnificent thing, which is say, okay, and we could derive and get this exactly right, I suppose, but hopefully you can kind of see this should work. The product C, we're trying to get to C, right? So C is then, we can take A and go in and multiply B1, the first column, and then the second column. Maybe make this, boom, we can get this one, right? And that will give us these new columns. So it's just A times a column, which this is itself a column vector, right? So this is, right, they have the same inner dimension, n and n, and then they have m by 1. That's the resultant thing. So this is a new column vector. Right, the whole thing is a column vector. And then that's the same for all of them. So this can be very powerful, right? This can be a very useful thing for us later on. So this is seeing, right, A times B, instead of a whole sequence of dot products, you can think of them as, in this case, there are k of them, k A times B situations. And we like A times B. That's a pretty good thing for us, right? That happens a lot, right? So that's good. And then we see that A gets involved in the final version of C in this way, right? So really, this first one here is a combination of A's columns, right? A times B is a combination of A's columns with the weights of B in there. This is again combinations of A's columns. So C only ends up with combinations of A columns, combinations of A's columns everywhere. That's an important thing. And if we go down in this direction, we're going to make row vectors. Right? We'll break A into its row vectors, and we get that same kind of structure that we had before, right? So that it's A times B. It's A's row vectors times B, A's, right? And they end up in the rows over here. So, and the way to think of this is that this says that C is made up of, right? So let me say this: C's rows are made up, right? Of B's rows. Linear combinations of B's rows. And over here, this says that C's columns are made up of A's columns. Nothing weird, like they don't get switched around in weird ways. So an example to work through that we've been using, it's getting pretty advanced here, right? So this is doing exactly what we just said. So going across in this direction, right? So we've got these two matrices, yeah? And if we want to, we can break B into its two columns and then pre-multiply by A in each one. So if you do this, right, this guy here, if you do that one, you get this. And if you do this one, however you want to do it, right, because this is a 2 by 3, this is a 3 by 1, and that's giving us a 2 by 1, so the dimensions are matching up, but we know it's, right, so we can just think again of the dot products of this row with this column, that gives us -3, this row with this column, that gives us -5, right, and so we get these two column vectors out, and that's the product, that's the result that we've had through this, that we've been working out from different approaches. Again, and we could do it this way, right? So we could say, okay, we're going to take the row vectors of A, multiply them in their entirety with in the entirety of B, and they will become the new row vectors. Do it like this, of the resultant matrix. And they've got the right form, right? So this is a 1 by 3, and this is a 3 by 2, and this is, of course, a 1 by 2 here, just this one. And this is a 1 by 2. If you work through it, same results. Now it's -3, 4, -5, 2, and of course, matrices and matrices, we get the same result. Boom. All right, so that's a good thing to understand in general, right? That this is a good piece of knowledge, right? So C's columns, whatever A and B are, C's columns are combinations of, this is just to sort of summarize what we've done, are combinations of A's columns, they're combinations of B's columns, given that there's this product A, B, right? The A is on the left and B is on the right. You have to think about it probably every time, but there you go. Back here, we had A times a vector, a column vector, of course, on the right, and a row vector on the left, and what that does. Right, so a column vector combines the columns of A, right, gives them weights, adds them up. The row vector on the left gives weights to the rows and adds them up, scrunches it down. Really important. And then there were these incredibly important, and we could do the block multiplication, that sort of feeds into everything there. There are these incredibly important structures here, so-called inner products and outer products, right? So the inner products, sort of everything's built out of that. And then the outer products are these kind of odd things that very important to see that they are, there's a lot of redundancy in them, right? So that all the rows are multiples of each other, all the columns are multiples of each other. But they will appear again and again. So that is some advanced matrix wrangling. And where are we? Yeah, so that's good. So the next thing, just keeps going, right, is inverses. And we'll see that, we'll get back to row operations and see how we can use them to do beautiful things. Okay.